Hello everybody, and welcome to another video on my channel. In our previous video, we covered a bunch of advanced trig integrals covering many different topics. And if you remember, in the series before the trig videos, we covered exponential and logarithm integrals. But there was one that I left out, and that is the integral of the natural logarithm of x. Now, in this video, that break comes to an end. We will prove the integral of natural logarithm of x and also learn about a very useful technique in a lot of integrals. So, without further ado, let's move on to the video. So what is integration by parts? Well, it really is what it says. You're integrating different parts of an integral by taking the derivative and also taking the integral of the different parts. And these different parts are the functions that multiply each other. But that does sound a little complicated. So let me write down the formula so you understand what I mean. This formula is u dv is equal to, the integral of u dv is equal to uv minus the integral of v du. Now this comes from the product rule, believe it or not. But before we go into proving it using the product rule, you can see what I mean. First, we're integrating the dv to get uv, then we integrate that dv, but we also differentiate the u to get v du, and then we take the integral of that. So, pretty much all it is taking a bunch of different integrals. So, now we know what we mean by integration by parts and how it works. Let's actually prove this thing. This all starts from the product rule, as I mentioned earlier. So, let's take the derivative with respect to x of uv, where u and v are different functions of x. This becomes uv dash plus vu dash. Now, what we do is we rearrange this. So, we get uv dash is equal to d by dx uv plus v u dash. Now, over here what we do is now we integrate. So integral u of v dash or dv by dx, and when we do the integral, we multiply by the differential dx, but in derivatives we divide by that differential essentially. So we get u dv is equal to, and sorry, this needs to be minus over here, is equal to uv minus, by the same process, v du. And there you have it. There is that integral we saw in this formula proved by the product rule. So now let's go on to prove the integral of the natural logarithm of x, thus essentially almost completing most of our basic functions to integrate. But we are not over yet, as there is still some more stuff, but those are more complicated and are beyond the scope of this channel. So this is effectively the final integral that we will be proving before moving on to methods to integrate stuff between other stuff, or like between these functions and combining these functions. So let's go. We'll start with our integral ln x dx. Now, over here, it says the integral of u dv. So it would make sense that we would assign a u and we would assign a dv. So, what are we going to do? Well, we know that dx would be perfect for dv because they both are differentials. So this is going to be our dv term, and this is going to be our u term. So let's integrate this. Now, what we have here is uv, so and integrating dx just gives us x, so x ln x, minus the integral of v, so x, times du. And if you've seen my differentiation series on calculus, you would know that this differentiation, or this derivatives, is 1 by x dx. So that's essentially it. And if you don't know what differentiation is or that stuff, I would like go off this video and go to watch that video first, as differentiation is pretty much required to know before you go into integration, and in these videos I assume you know differentiation. So integrating this right hand side gets us x ln x minus x plus c, and that becomes the integral of this function. So there you have it. You have the integration by parts, you have the product rule, and the integration by parts proved using the product rule, and the fact that we have proved ln x dx as an example. Now, just one more problem solving tip before we move on to our singular example of this video, as this guided example of ln x is actually very good to show how u and v are assigned, and if necessary, how one must do it again, as it's very simple, as you just take this integral and re-plug in the formula. So one final problem solving tip is u is good for x to the n terms, or e to the x type terms, because number one, let's say you have to do it again and again, you're going to be integrating that u more and more until you pretty much get only v. So that's why u is very useful, as the more and more you do it, the more and more it decays until it essentially becomes not important as part of the equation. And the reason it's e to the x is also useful is because it's cyclical, because it goes e to the x, then e to the x, it just loops its own integral. And that property is really going to be demonstrated in this next example, where I'm going to show you why and how we use this problem solving tip, and what to do if any amount of repetitions doesn't seem enough. In this example over here, we have the integral of e to the x sine of x dx. So let's integrate it. So what we do first is, as I showed in my ln x example, is we substitute what we have for u and dv. Now, as I said earlier, this would be good for u because it's an e to the x term, and that leads sine to the x dx for the dv term. Now, what we're going to do is we're just going to apply the formula. So this is equal to e to the x, minus e to the x cosine of x, because integrating sine of x gets you negative cosine of x. Then you have minus the integral of v, so again negative cosine of x, so this becomes positive, and then the integral of e to the x is just e to the x, so plus e to the x cosine of x dx. So, but now we have another integral, so we do the other tip. We repeat the process. This is u and this is dv. So this becomes negative e to the x cosine of x plus e to the x sine of x minus the integral of e to the x sine of x. Now this is confusing because we just have our integral back again. So what are we going to do now? Well, now what we have to do is go back to our original equation and what it looks like right now. So we have the integral of e to the x sine of x dx is equal to e to the x sine of x minus cosine of x. So there you have that, and then minus the integral of e to the x sine of x dx. Now normally it would be a problem because this would just go on forever and ever and ever. But what we can do is we can just add this integral to both sides. So we get 2 times the integral of e to the x sine of x dx is equal to e to the x sine of x minus cosine of x. And from the fact that we get this, we can divide it by 2, and that gets us the integral of e to the x sine of x dx is equal to e to the x sine of x minus cosine of x divided by 2 plus c. And there you have it. That is the integral answer for this problem. And as you can see, it actually required a little bit of problem solving creativity, as if you had just tried to solve the integral with brute force, you would have just been stuck in this loop forever and ever. But with this technique, you realize that you must look at the equation as a whole before moving forward, and that allowed us to find this very neat solution to this integral. So if you found this video fun, educational, or helpful, please make sure to like, subscribe, and hit that notification button for more awesome videos just like this. Thank you so much for watching this video. You guys are the best part of what I do. See you in the next one, and bye-bye.